Hello everyone, welcome to this video. In this video, we will be discussing a few questions of graphs, and this video is actually continuation of the previous one. In that previous video, we introduced graphs as a data structure to you, and we did a few basic traversals of that to give you a clear understanding of how graph can be manipulated. And in this video, we are going to be picking up from the same point. We will be discussing a few basic questions of graph in which we are going to be dealing with different sorts of graph. You're going to see further what questions we have taken. And once you are done with all these questions, then you will be confident enough to tackle higher level problems. So for getting a head start in this video, stay till the end and let us begin with the first problem. Okay, so the first question that I've picked up for you is check if path exists between source and destination. One of the very simple and basic questions of graph. The user will be giving you two nodes. One is going to be the source, other is going to be the destination, and you need to return a bool value. What is a bool value? Either true or false. You need to just tell whether there is any path in between these two nodes or not. Okay, so if you are if you're able to configure that this graph is actually directed and acyclic graph. Okay, what does that mean? Well, directed graph means that the edges that we have here actually are directed. That means if we are standing here at A, we can go to B, but we cannot come back to A. All right, because this is only one direction we can travel in. So, and what do we mean by acyclic? That means there is no cycle being formed in this graph. Okay, so even if you see this situation, which might seem like a cycle, but because the edges are directed, so you can see D is going to G and then we can travel from G to H, and this is the other path from F to E and E to H. Okay, there is no loop here. That means we are dealing with a directed and acyclic graph. All right, now let's quickly make up the adjacency list of this. I'll be using one hash map sort of a data structure, specifically dictionaries of Python. You can take any relevant data structure that you find suitable. I have already made up these keys. Now let's see what are going to be the edges. So A, what are the neighbors of A? B and C, right? These two. Then quickly, what are the neighbors of B? F and D. Then for C, if you want to see, C does not have any further neighbors. That means I'm going to put empty list here. Then for D, it has two neighbors, G and I. Right? Talking about E here. E has only one neighbor, that is H. For F, if we see that, we have E. And for G, we have H. For H, we have nothing. For I, we have nothing. All right, so this is our adjacency list that is formed. Fine. Now, how we are going to approach this question? Let's first take an example. Okay, let's check that the source is A, and I want to check it for G. Fine. I want to check between A and G. A is my source, G is my destination, if there is a path existing between these or not. Okay, so we are going to be thinking of a recursive logic. All right, and let's focus precisely. Let's think it in a DFS manner. What is DFS manner? We are going to pick up one direction, explore our neighbors of it, then in each and every direction we have to go and explore further nodes, right? But we do not have to change the direction unless all the possible paths are exhausted. What do I mean by that? Let's see it in the diagram. I'm here. This is my source, and let me just mark up my destination as well. Destination is this one. All right. So destination, this is my source. My logic would be something like, I am here at A. I can only see these two neighbors. That means B and C. I can only interact with these two neighbors. What I can ask to these two neighbors so that I can figure out my answer? I can ask from B that is there any path to H through you? Okay, I'm asking this question to B. That means I am asking B, if you were source, Do you have any path to the destination, to H? B can answer again in two terms, either yes or no, that means true or false, correct? And C can answer in two terms as well, true or false. Well, as we can see here, because we have just drawn a diagram, we can see yes, B would be finally giving true and C is giving false, correct? Just think of this scenario. A is receiving two answers, true and false. Through B it is true, through C it is false. What should be the final answer that A must give? Can we reach H through A? Yes, surely we can. We can take up this B path, right? So no matter all the answers that A is getting, if A is getting just one true, then we can say that we can reach from A to H, right? Okay, so I know that A has two neighbors. One of the neighbors said true, other neighbor said false. We have to take OR of it. Okay, so no matter how many neighbors are there, even if you can reach to the destination through any of the neighbor, the answer is going to be true finally. Fine. Now we figured out this situation. What is going to be happening internally? What is going to be happening internally? B still has two more nodes, right? B has two more neighbors. B will do the same thing because we are breaking down the problem, right? In the recursive manner, B will ask the same question to F and D, right? Luckily for B, it will get true from both the sides, correct? But how? From where the answer is originating? Let's take up this path. I've taken F. F will ask the same question to E, and E will ask the same question to H. Now when E is asking the same question to H, that means can I reach through H? Can I reach to H through this node, through this neighbor? Well, we are actually standing on that. That means this is our base condition. What is the base condition? When the source itself becomes the destination. This is the base condition. Okay, we are going to be traveling through the neighbors unless we are encountering this particular condition. Once we get till here, that means I am standing at destination, then finally I can return true. This is the origin of your answer. Okay, and this is going to be completely tracked to my main call. So H from here has sent true, right? E, because E now knows that E can reach, like through E you can reach H. So what will you do? You will pass on this true here, right? And this true will be passed on here, and further B will be getting the answer. Same, like similarly, when we branch through D, D will ask the same question to I and the same question to G. I will return false, right? Because it cannot reach to H. G will make call to H. Again, the base condition is hit. Then it will return true. This true will be returned here, and this true will be returned here. Correct? Now B will be receiving two trues, and what will you do? You will again do true or true, because at every point, at every condition, at every node, we are taking all the answers, we are taking all of that, and we are giving the final answer. This is what we are doing. So I hope now you have a little idea about what we are doing in this question. Let's just simply see the algorithm for it. Okay, just clearing the input. In input, you are given the graph. Actually, I've already formed a graph for you. As we have drawn this here, I've already done that in code as well. And the input that you would be getting from the user is going to be the source and the destination. Fine. Then what you have to give as output? Either true or false, if the path exists or not. Okay, so this is the recursive algorithm. To design a recursive function, base case is this. As simply that we have discussed, if source becomes a destination, we need to return true. Correct? Then I'm going to use a bool variable to keep track of DFS calls, DFS call responses, and I've named it as answer. Done. After that, what do I have to do? I have to make calls to the neighbor. That means whenever, like where at whatsoever node I'm standing, beginning from A, I have to make calls to all of my neighbors, and they will be giving me some answer. Correct? This is what we have to do here. Once the call is done and we have tracked the answer in this variable, we are going to return the answer here. Fine. Okay, now let's see the code for it. Okay, what we're doing here, I've taken this graph here, correct? I have taken input from the user and I've gotten my source and destination. Now I'm calling this function. What it'll give? It'll give a bool value, true or false. When we come here, what I've done, I've just written this base condition. I've said if my source becomes destination, if source equals destination, I'll return true. Else, I will create one answer variable, and initially, I am just putting false value there. So after we encounter these two lines, we will know how we are working and what we are doing with answer. So what I'm doing here is I've said for neighbor in graph source. That means if I'm standing at A, I'm going to be calling the same function, the same hash path function to all of its neighbors. Similarly, if I'm standing in B, I'd be calling the hash path function to all of the neighbors of B, right? And whatsoever answer is the neighbors are giving us. Let's take condition of A only. From B, when we have called this same function on B, B returned true. So the condition was answer equals false or true, right? Answer has become true now. After this condition, C will return false. Answer is true, we'll do true or false. The answer will be true, correct? So eventually, for the first call, for the main one, if we see, we'll be receiving true as the answer and we are going to return that, correct? I've taken this scenario of A, you can take any scenario of any node. Only this is the thing that will be happening internally. Okay, I hope you have understood this question now. Let's try to run this question. Let's try to run this code. Okay, here's the same code written. Let me say I want my path from I to G, right? Actually, there is one catch. Just give me a second, guys. Yeah. So the explanation that we were having, I started that with A and G, and I actually calculated it for A and H. So obviously for G as well, we have the paths and we can reach it. The answer for this one is also going to be true, but the dry run that I did with you is actually for AH, right? I hope you have figured that out already. Let's run this here. Okay, now so if I have to give A and H, first check for that, then we'll check for A and G. Let's try to run that. Okay, so the answer we are getting is true, correct? Now let's give A and G and see if the path that we are talking about exists between A and G or not. Okay, answer again is true. That means the answer between A and G also exists. So I hope now you have clear understanding of how this question is working. Let's quickly move towards the next question now. All right. Okay. So again, you might think the question statement is same, but believe me, the graph is slightly different if you notice carefully. We are again saying check if path exists between source and destination, but this time the graph has become undirected. This time the graph has become undirected and it might contain cycles as well. How are we going to avoid it? Right? Now, this is just another type of graph that is very common for you to encounter when you are solving graph problems. Fine. So I have created the adjacency list here. You can just check A is having two neighbors, B and C. We have it there. Now B is having 3 neighbors. Be very careful. B is now having A, F and D as neighbor because we do not have directions here. So if we just see B, in the previous condition, it was like this. It was directed. So B only had 2 outward edges, but this time we do not have the direction. That means B is having 3 edges and 3 neighbors. Okay. And similarly, in the same manner, I have constructed this adjacency list here. Now, what is the modification that we have to make? What is the modification that we have to make from the previous question? Obviously, the previous code can be mapped to it, but what is the addition? See, if you're in the condition that we are here at A I have again, let's take again the same example of A and H. I will say that can I reach to H through B? I'll ask the question to B. The question will go here, correct? And I'll ask the same question to C as well. But for let's take the condition for B. I've asked the same question to B. Now B, because we are following a recursive approach, B will also ask the same question to all of its neighbors. It will ask the same question to F, it will ask the same question to D, and because this time A is also a neighbor, B will also ask the same question to A. Will this lead to our answer? A will be asking to B that do you have the answer? Can we reach to H through you? And B is asking the same question back. Can we reach to H through you? Obviously we cannot, right? This is the part we have to handle. How are we going to handle that? Here is the concept of visited comes to play. What do we have to do? We have to maintain one data structure in which we will keep a track of all the nodes that we have gone to already. That means once we have stepped on one of the node, that is visited. So initially we were standing on A and we were asking questions, A was visited. When we went to B and B started started questioning its neighbors, B was visited, right? Now, once I'm standing at B and asking to my neighbors that can we reach to H? Can we reach to H? Once comes the chance of A, we will already see that A is already visited. If A is already visited, we would not waste our time asking the same question to A, right? In this manner, we would avoid the situation that we were facing, and simply the working that we have seen in the previous question, the same working will be happening here. Let's see the algorithm for that. Let's see the algorithm for it. Okay. Again, point to notice here. Again, you have two things. You have graph, you have source and destination, and you have to return true or false. What is written here? Main point, please remember, we need to keep a track of visited nodes. This is done using a data structure, which is called as visited, or you can simply say viz or visited, whatsoever you want to name it. You must know what is the logic behind it, why we are taking that. Usually we take one set. You can also take vectors or any of the data structure that is suitable for your question, for keeping track of it. You can even take a 2D matrix if you are dealing with matrix questions. All right. So here is the algorithm. You can see the whole algorithm is same, but only two lines are different. The lines in red. That means this one and this one. What we are doing here is, again, the same base condition is there, that if the source becomes the destination, we are going to return true. And this is the second point, then that once we are beginning to work on first node, that means if we are there on A and we are starting, we are going to just start asking the question to the neighbors. Before asking, we have to mark it visited. That is what we are doing here. We are just marking the node visited. Fine. Now what do I have to do? Again, I'll just I'll create a bool variable which will be helping me to keep track of my responses, of the responses that I'm getting from neighbors. Then I would be making calls to the neighbors along with a check that the neighbor I am making call to is actually not visited already. Fine. Once this working will be done, the recursion tree will be over. Eventually, I'll be having the answer in this variable and I'll just return that. Okay. Let's try running this code as well. Okay, so here we have the code. As you can see, we have our graph made here in the form of a dictionary. And I am taking ABCD, that means alphabets, for my nodes. Usually in the questions that you would be encountering during your problem solving might not be the same. It could be numbers as well, but that actually does not matter. What matters is that you are focusing on the concept of TFS, and then you'd be able to create up your own graphs. We'll also see a variation of that, don't worry. Let's focus on DFS here. Okay, so what is the modified thing that we have done? I have introduced one visited set here. Okay, I have my visited set here and I've called this function. You must take it from the user. Just for the sake of running this program, I gave it on my own. you can take input from the user for your source and destination node. This is the first parameter is my source, the second parameter is my destination. Along with that, I'm passing graphs and visited in this call, okay, to this function. So what is happening in this function? It is completely mapped to the previous question. Just 2 lines are added. The base case is the same. We are adding the source where we are standing. We are adding the source to the visited. Then what we are doing, I'm creating one Boolean variable. I've initialized with false. Then I am traveling to each and every neighbor of that, each and every neighbor of the source. What I'm doing there is I'm checking that if my neighbor is not in visited, okay, that is not not already visited, then what I'll do is I'll make the call and I'll just store the answer in answer variable just by simultaneously doing OR with the previous values. Okay, once that is done, I'll be returning the final answer. Let's try to run it with a few examples. Again, for the same one, let's do for A and H. Do we have a path here? Yes, we do. Correct. Any other example? I want to say, do I have a path from A to, let's say, C now, or C will be just 1. So let's check A to I now. See, true, correct? So I hope now you understand both of this question thoroughly. Let's do one more question, and I would be expecting you guys to code it yourself. So here is the third question. The third question is number of provinces. Okay, so you can read the problem statement from GFG practice. I'll explain you the problem here. What is happening here? You will be receiving one graph, okay, and I'm saying it to be one graph. You might be thinking that these are 4 different graphs, but no. As per the question, it will be giving you only one graph. What you have to do is you need to return the number of provinces. In other words, we can say you need to return the number of components. So what you might be thinking of separate graphs are actually components of one single graph. Just the thing is, they do not have any connecting edges. Okay, because they do not have any connecting edges, we are calling them separate components. Okay, and what is your role in this question? You have to calculate the number of provinces, in other words, number of components. Okay, now what was the usual format that you are given graphs? Usually you will be given one vertex V and you will be given one data structure for edges. This is the usual case. I'll tell you one more case as well. So in vertices, what will happen? It actually is just an integer. So if you are given V as 5, then the vertices that you actually are having are going to be 1, 2, 3, 4 and 5. The integer means that all the nodes are from 1 till that number. Okay, so these are all the nodes that you have in the graph. For this one, the maximum number is 10. So the V actually is 10. That you'd be given V as 10. You have to understand that we are actually talking about 10 vertices. And 10. Okay, you have this information. Along with this, you know what edges are given. Edges would be given in pairs. So assume you have this edge 1 3 3 7 1 7. So it will be given 1 3 1 7 3 7. Fine. Okay, and similarly you have 4 9, then you have 8 5, 8 6, 5 10 and 10 6. Okay, you have all the edges now. You will be given this information. Out of this information, you need to make up your own graph. Okay, you can form a hash map, that is your dictionary, or you can do it with vectors if you're using C++ as well, right? It is up to you how you are thinking of the graph, because it can be implemented in various ways. The most common one is making up an adjacency list. That can be done through either your hash map or vector. I'm using a dictionary here. You can use any of the data structure which you which is suitable for you. Fine. Now, how will you be dealing with this question? What is the logic behind it? You know, like till here, if you are following the videos, I am assuming that you are very clear with DFS and you also have knowledge of BFS, right? So we are very clear with these two concepts and how we can travel the graphs and we can figure out whatsoever is being asked from the graph. This time we do have to perform the traversals as well. But in what manner? What is the logic? Well, look at the diagram now. If I say, I will start traversing, that means assume I am standing here at 1. Correct? I encountered 1. I can say that, okay, I have encountered one node. That means it is going to be associated with one whole component, right? Once I encounter one node, I will say that please increase the counter. Okay, I have just said a counter equals to 0 and this is counting your answer. That means counting number of provinces. I'll say increase it plus 1. Fine. Now what is going to be my duty so that no other node of that components will be doing the same thing. What did 1 do? 1 increased the count. But 1 has increased the count on behalf of the whole component. So what do we have to do to avoid traveling this component again? We have just seen the similar situation in the previous question when we were avoiding the calls using visited. Once I stepped on 1, I will call one DFS function. What will that DFS function do? That DFS function will go to each and every node present in that particular component and will mark it as visited. So it will be visited, it will be visited, and it will be visited. Done? Okay. Similarly, we are going to be calling with 2. We are done with 1. I'm going to be doing the same thing with 2. I will check, is 2 already visited? No. So I can call the DFS function here and I can increase my counter as well. Correct? Because that is a separate component. Because it is not already visited, that means it is our next component. I'm going to plus 1 here and I'm going to call the DFS. It is not actually like having further nodes. It will be marked visited and our work will be done. Now comes the condition for 3. Now comes the turn of 3. Once we'll go to 3, 3 is actually already visited. We need not to count or we need not to call the function DFS here. That means 3's work is done. I'll go to 4. What will happen with 4? Counter will be increased. Counter will be increased here. And this 4 will be marked as traveled, that means visited. And this 9 will be also marked as visited. Just by doing the same thing, calling a recursive function, it will be breaking down the problem and will be marking everything as visited. Just like the previous questions we have been seeing. Fine. Okay. Now once this is done, after 4 will come the turn of 5. 5 again is not visited. What will happen with 5? It will increase the counter and it will mark 5 visited and all the nodes associated with it as visited. That's also done. After 5 will come the turn of 6. We'll avoid the count, we'll avoid the call. So, after that 7, same thing. 8 already visited. 9 already visited. 10 already visited. Okay. Eventually, what is present in my counter? My counter is having 4 as the value. Okay. And 4 is actually what? The number of provinces. We need to return this 4. Fine. Okay. If you have to see, let's just take a quick look to the approach. The approach is saying make use of visited. We have seen how. I'll loop from 1 to 10. That means for this question, we are giving v equals 10. I'm going to be just using a loop which will be going from 1 to 10. And what will I do? At every, let's say we are using I here. So if my I is not in visited, okay, what will I do? I will simply make the call to DFS. DFS will be taking up that I, it will be taking up the graph that you have made and it will be taking up visited. And once you enter the DFS, what it will do? It will simply add I to visited, that is going to be the first thing, and it will be making call to all of its neighbors, and it will be making them visited as well, that if they are not already visited, we will call the DSS function on them, and this thing will be happening to completely visit a component. All right, so I hope you have understood this question very clearly and you can attempt the code on your own. One thing more I must tell you about this question, that if you're going to go to practice session to solve this question, you will be receiving an adjacency matrix. That means it is going to be something like this. So if I say v equals 3, you'll be having 0, 1, 2, 0, 1, 2 as a matrix, because v equals 3 means you will be getting 3 cross 3 matrix. So if I make up a diagram like this, right? So what is happening here? We are having one edge between 1 and 2. So it is going to be 1 and 2 having one edge, 2 and 1 having one edge, correct? And no other edge is there. So we can mark every other value as 0. Fine. Now once you have this matrix, once you are present with this matrix, you can figure out and you can make up, either you can start working with this and using this logic, or you can first convert it to adjacency list, because you might be more familiar and more, comfortable with it. So up to you. You can directly start implementing your logic with this format of graph, or you can convert it to adjacency list and then do the following that we have discussed. Okay. So I hope these 3 questions were helpful for you. These are for making your graph pedestal strong. Further ahead, you have to try much more questions to be proficient in graph. And if you found the video helpful, don't forget to mention that in the comments and do like the video. And thank you so much. Keep coding, guys.